So, in conclusion about our models, this is where we think that the universe has gone over the last 13.7 billion years. Now, I don't want, even if you just slept through half of this, I don't want you to go away not realizing some amazing stuff has gone on. So let me try to very quickly recapture the amazing stuff that's gone on. And where we now know, because let's see for a second something. We now know we sit on this very small ball that we call Earth in this very big universe. And yet, with our relatively, in terms of scale, our relatively small sized brains, even if we aggregate the entire volume of all our brains together, it's really small. And yet we've been able to figure out, without really ever leaving this planet, because almost everything that I've talked about tonight, we know by making observations with telescopes sitting on the planet, some with telescopes in space. How far in space? A couple of 100 miles. They're, in the scale of the universe, it's nothing. It's absolutely zero. Even if you go to Mars, it's just no distance at all. So everything we know about our universe basically happens because we're able to sit on this planet, make a certain number of observations, and come up with self-consistent laws which explain, up to a point, the way our universe looks. So we think that the universe started in this Big Bang 13.7 billion years ago. We think that it expanded very quickly. I didn't mention this part, but this is the only part which we didn't mention. And then, as time goes on, the universe, it's getting a little bit bigger, not too much, but then, all of a sudden, it's starting to really take off. So for a lot of its history, the universe was expanding gently. At the very beginning, it expanded very quickly, then it expanded gently, and then now it's really beginning to rev up again. And the scary thing is, we don't know what happens to this. We have no idea. This will kind of go, and zip, we could all be blown apart tomorrow. So, we might reach some critical size in the universe, and all of a sudden the universe just decides, okay, that's it. And that, so we don't actually know. So we don't actually, any line that projects forward is a guess, because we don't know what's causing it. We call it dark energy. We don't know what's causing it. So we don't know what's going to happen to the next bit. This diagram we didn't know in this detail at all 20 years ago. We had a different diagram 20 years ago. So let's not be too arrogant about where we think the universe is going to go. But really interestingly, we do have a model. And we see that stars and so on get born and they get reborn, they build planets and all of that type of things. And this is where we basically are today. And then there's a big sort of question mark that you can imagine about where we're going and what's going to happen next. So we know this, but are we the only universe? So if we ask two questions. One, where are we going? Does this curve continue? What does it do? Does it even fall back on itself? Maybe it does fall back on itself. We don't know. Does dark energy get tired? Does it get stronger? We don't yet know the answer to that. But we can ask lots of other questions. Why is gravity attractive? And I'm glad it is, because otherwise it'd be a bit awkward if it was repulsive. Why is it the strength it is? Why is it not more? Why is the value it is? Why does light travel at the speed of light? Well, obviously light is going to travel at the speed of light. That happens to be 3 by 10 to the 8 meters per second. And here's the thing, when I went to college, people say the speed of light 3 by 10 to the 8 meters per second. And I remember thinking, why is it 3 by 10? Why is it that number? And I was too afraid to ask. It was years later that I thought, why is it 3 by 10 to the 8 meters per second? Why is it 3,000 meters per second? Why? Come back in just 1 second. Almost finished. But it's a good question. Why? Why are atoms stable? So you might think, well, of course they're stable. Well, that's not obvious. So if you look inside, if you think about the atoms in your body, the atoms in anything, by the way. I often say in your body, but they don't have to be in your body. They're just there, they're just there, they just are. And we know that there's kind of a nucleus and electrons going around those. But if you actually look at it, the nucleus is incredibly finely balanced. If you were to look at the balance on that, it's more unlikely that a nucleus is balanced in terms of forces to hold it just together. What's the two options way? If it's unbalanced, it could break apart or it could collapse in on itself. But it just stays nicely there. It just stays nicely stable, most nuclei. Radioactive is a bit of a counterexample, there's a good reason why. But most nuclei stay good and solid for billions of years, thankfully. Why? There is no good reason why that needs to be the case. In fact, the probability that nuclei are unstable is much higher. It's easier to make unstable nuclei than stable nuclei. So one of the things that might be the case is that in our universe, one of maybe an infinite number of universes, these things just are the numbers they are. In another universe, the numbers associated with these things are different. So gravity, maybe in some universes, it's much weaker. Maybe it's repulsive in some universes. If it's repulsive, you can't build planets. So in those universes, there's no planets, there's no stars, because gravity pulls stuff together to make planets and stars. In those universes, maybe things are much stronger, so you weigh more, or less, you weigh less. In other universes, maybe the speed of light is some completely different number altogether. In other universes, maybe atoms aren't stable. In those universes, again, you don't build interesting things. You can't build big long chain molecules that make up you and me. These are not so, from our perspective at least, the first order, are not such interesting universes. So we live in a universe where things are kind of nicely balanced. That's a great place to be. But we also know, actually let me just, before that's my last slide, we also know the following. If you, or at least we think we know the following, I'm very careful with this one. If you think if we go back to asking questions in our classrooms, we have models which we've had to keep on changing. And in recent times, we've built up a model of the universe. But that model encourages us to ask other questions, fundamental questions about the role of our universe. So when people say to you, if your pupils say to you, but why is the sun the size it is? In a way, there is no answer to that. In our universe, it just so happens that gravity is a balance between that and the pressure that you get from heat and so on. That the equations just make stars that are kind of like that in this universe. But in other universes, this may not be the case. But coming back to my penultimate point, one of the things I think that's also the universe tells us, and I always think this is really interesting because we talk about the model as if it's kind of an inanimate thing, but to the best of what we can say, with our current knowledge of the universe, most of the universe doesn't know it exists. So you and me, if we're not sleeping, do know that we exist. This is an amazing thing to be in a universe. The vast majority of the universe is not able to understand itself. We are. So philosophically even, the fact that we have consciousness, that somehow our molecules put themselves together and whatever else has to happen, and that gets into all sorts of potential philosophical and other discussions. But the net result, irrespective of how those discussions get moderated, are that we're incredibly lucky to have been able to understand what we just discussed tonight. To be part of understanding that and being part of figuring that out. That's a privilege. That's something that astronomy tells us. So our building of the model of the universe fundamentally tells us that we're special and that we need to look at, well, we don't have to, but I think it tells us that you have to look after each other. That for me is one of the unexpected outcomes of trying to build what you might consider a physics or chemistry based model of the universe. And it's encapsulated much better by Carl Sagan. Every one of us is, in the cosmic perspective, precious. If a human disagrees with you, let him or her live. In 100 billion galaxies, you will not find another. And another The final quote: imagination will often carry us to worlds that never were, but without it, we go nowhere. And I think what that tells us is the history of the modelling of our universe, that every time we think we know, there's some new interesting twist. Maybe that won't go on forever. But with dark energy and dark matter, we're definitely in a twist situation at the moment, and we instantly see how that's going to play out. But it also tells us that we live in a universe which is inherently against us, and yet we survive, and yet we thrive. So let's not be the architects of ourselves throwing that away, because we've been given such an amazing opportunity in such a large universe to look after what we have, and we should really grasp that. And for me, I'd always want to get that thought across to our students as well, because otherwise it just becomes a lesson in circles and ellipses and that type of thing. And it's so much more the story of who we are, and that's why modelling our universe is really important to understand. So I've gone on a bit longer than I intended, but thank you all for staying for so long. I really appreciate it.